Team 6 and our super original project title is face mask detection. I'm super excited to showcase what our team has been working on these past couple of weeks. Now without further ado, let's go to the next slide and get started. This slide highlights our plan for this presentation. We will start off by discussing the problem we're trying to tackle, as well as a proposed solution to it. Since we are proposing a machine learning focused solution, we will also spend some time discussing the dataset and what it is comprised of. After this intro, in the next section, our team members will take individual deep dives into their respective models and showcase each one. This overview will consist of everything from a high-level description of the model to an intricate analysis of the performance on our selected dataset. We'll then round off the presentation with our future plans and where we plan to be in the coming weeks. After discussing our future work, we'll discuss the conclusions and takeaways from the presentation and open the floor up to questions. So with that being said, let's jump into our first section and discuss the disease we're trying to tackle, as well as our overall approach. My name is Athray Anand, and today I'll be guiding you guys through the disease we are focusing our project around and providing some of the motivation that went into our work. As I'm sure you have guessed by now, the disease we are talking about is none other than our best friend COVID-19, also known as the coronavirus. The virus was first reported around December of 2019 in Wuhan, China, and since then, and has been spotted in every nook and cranny of the world. To date, the virus is responsible for 50.5 million cases of infection worldwide and a whopping 1.26 million deaths. Although this is extremely disheartening, the scarier thing is that the virus is not going anywhere for a while. Even if a vaccine was announced tomorrow, it would take months or even years to roll out to the mass population and even longer to develop widespread immunity. The best approach we can currently take is active prevention and precaution. The coronavirus, or COVID-19, is officially noted as a global pandemic by the WHO due to its contagiousness. As I'm sure you know, the primary means of COVID spread is human-to-human contact. It spreads through what the CDC calls respiratory droplets, or small particles, similar to the ones you see from aerosol spray cans. These droplets are produced when an infected person coughs, sneezes, sings, talks, or even just breathes. They can be inhaled by a bystander through any of their air passageways and cause infection. Similarly, droplets can also land on surfaces and objects and be transferred by touch. So what else can we possibly do besides standing 6 feet apart from one another? You guessed it, you can wear your mask like you're supposed to. According to IHME, if 95% of the United States population began wearing masks, the expected death toll would drop by an impressive 50%. Actively preventing the spread of the virus by precautionary measures such as wearing your mask and socially distancing is key to making our lives as normal as possible. I'm sure you have all heard of the saying, flatten the curve, and how crucial it is to prevent ourselves from promoting the spread of the virus. Even if it has a low chance of affecting us, it is our moral responsibility to protect those vulnerable around us and decrease the overall rate of infection. You have probably noticed that every store and establishment now has a mask mandate in place enforcing the use of masks in exchange for whatever specific service. It is safe to say that our mask collection has become a part of our wardrobes. Finally, the success and financial livelihood of small businesses relies on our diligence in wearing masks and social distancing. Without a stimulus in the past several weeks, small businesses are more reliant on our support. If we don't take the precautionary measures, another surge of national shutdowns will crumble the livelihoods of thousands, if not millions. Now, with that being said, let me hand it off to my teammates to walk you through our approach.
A report from the Institute for Health Metrics and Evaluation also emphasized on the importance of wearing a mask. It says that in the report, if 95% of the US population began wearing masks, the expected death toll will drop by 50%. So, the project is intended to identify an efficient means using the computer vision and deep learning methods to identify proper mask wearing such that it can be implemented effectively into real-world institutions to help everybody survive this epidemic. For the datasets, mainly we used 3 kinds of different datasets. The first one is the Kaggle face mask detection datasets. 853 images belonging to 3 classes exist in this dataset. All of the images are labeled into three classes, with mask, mask weared incorrectly, without mask. The total size of this dataset is 388 MB. The second and the third dataset are the masked face left dataset and the self-collected dataset collected by ourselves. Tianyi will give you more details on these two datasets.
One of the major things we wanted to cover in our project was not only face mask detection, but also incorrectly worn face masks. So as we all probably know by now, masks are only really most effective when they are completely covering your mouth and your nose. And so in our research for this topic, we had seen many papers that covered mask detection, but not very many that had also covered the case of incorrectly worn face masks. And we felt that incorrectly worn face masks are a very important case to consider, right? Because we don't want people running around with their faces not properly covered. So another use case we wanted to cover was potential malicious users. So some companies, such as Uber, we found, are requiring users to complete a face scan to basically prove that they're wearing a mask. So we're foreseeing that there could be some malicious users that try to circumvent these algorithms by doing things like covering their face with their hand or their shirt, like I've done in these examples. And I would argue that these examples could defeat an algorithm that was trained only to see that the mouth and nose were covered. Right. So we want to try to create an algorithm that is robust against attacks like these. So I just wanted to go over a few of our data sets that we have here. So one data set that we managed to find contained over 60,000 images each of correctly and incorrectly worn masks. And I've included some sample images here, and you'll see that there are examples of people wearing masks over just their mouth or like just under their chin, right? Which is exactly what we need. And you might notice that the masks might look kind of funny, and and that's because they are computer generated mask images. And so we felt that even though these aren't real use case images, we can still utilize these to help train our models.
Now we are going to present the two models that we have explored so far to detect face masks. The first is faster RCNN and the second is single shot detector.
The face mask detection system can be used in a lot of public areas like hospitals, airports, and offices. For example, in the airport, face data of travelers can be captured in the system at the entrance. If a traveler is found to be without a mask, their picture is sent to the airport authorities so that they could take quick action. If the person's face is already stored, like the face of an airport worker, the system can send the alert to the worker's phone directly to remind him to wear his mask.
For our training process, even though we have multiple models, each model was trained on more or less the same process. To train our models, we first split our data set into training and test and set the hyperparameters. Then, with our training set, we run through the training loop. The training loop starts by forward propagating through the convolutional neural network model, which will generate a prediction for each training image. We then compare the predictions with the ground truth and calculate the cross-entropy loss. After computing the loss, we will backpropagate through the network and update the parameters and again start back at the top of the loop. This training loop is done a number of times defined by our hyperparameters, and after all the iterations are done, we perform validation on the aforementioned test dataset.
Hi, my name is Divyanshu Preti, and I'm going to be talking about our first model, that is Faster RCNN. RCNN is short for Region-Based Convolutional Neural Network. The main idea is composed of two steps. First, using selective search, it identifies a manageable number of bounding boxes in the image, which is usually about 2000 bounding boxes, which are called region of interests or ROI. It then extracts CNN features from each region independently for classification. As shown in the figure, the model first identifies potential regions that can contain objects and then run a CNN trainer on each segmentation for classification. This approach is obviously very slow. This is solved by fast RCNN, which unifies three kinds of computing into one. That is CNN for feature extraction, SVM classifier for object detection, and bounding box regression. This model still depends on a separate region proposal network which is independent. By integrating this region proposal network into the fast RCNN model, the model becomes even faster, and hence it is called faster RCNN. We first sampled a random sample of size 10% from the available Kaggle data to be used as testing data. We then fine-tuned the model on the training data with the bounding boxes and the ground truth labels. We used ResNet 50 RCNN image segmentation model provided by PyTorch, which is pre-trained on the COCO dataset. We then used stochastic gradient descent and the loss function built into the model to train for 30 epochs. We were able to achieve an accuracy of 58.33% on the test data and a precision of 85.71% and a recall of 60%. The average prediction time for the test image was 15 milliseconds. In our predicted images, we used the following labels. The correct mask is indicated by a green box, the incorrect mask by a yellow box, and a no mask by a blue box. So some of the easy cases are those that have a clear boundary and segmentation of the area of the mask. However, there are cases where an incorrectly worn mask is classified as no mask, as is the case in the right image. The images that contain a lot of masks with small bounded boxes seem to form the majority of the edge cases. For example, in the left image, the model misses the man who is not facing the camera. And in the right image, the model misclassifies in case a person is holding a cloth to their mouths or assigns two labels to the same bounding box. In the future, we want to improve upon the performance of this model on edge cases, especially for incorrectly worn masks. We also want to get more data and test the model on real-time images from a camera. I'm going to take you through the code walkthrough for our faster RCNN model. So let us see how we take the input. So we want to use PyTorch's data loader model, which expects a dataset class that defines one method called getItem that defines how to get the data point at the time of training and testing. So here we can see our data item method. We also see that we are transforming both the images and the labels to tensors. And the getItem method then returns both the image and the corresponding bounding boxes called target here. So here we have defined a method which actually loads the data. So it takes as input a fraction, which would be the fraction of the test data that we want to take out of the total data. It defines a transformer which converts all the data to tensors. Uh, we also use PyTorch's random split utility to randomly divide training and testing data into two fractions. And this method then returns an objects for both test and training that can be iterated over to get the corresponding training and testing data. Finally, we call this function and we specify 10% as the testing split. Here we have our model training. In total, we have total 30 epochs, and we select the hyperparameters through manual searching where we manually change the hyperparameters until we get the optimal results. In each epoch iteration, we sum up the total loss, which we can see decreases over subsequent epochs. So here we have our testing module. We start off by initializing all the variables as 0. We then iterate over test data one image at a time and get their predictions from the trained model. Each predicted bounding box is compared with all the target bounding boxes, and intersection over union is calculated. The bounding box that has more than 50% intersection with a target bounding box is selected for comparison. This bounding box's label is then compared to the target label and classified as true positive, true negative, false positive, or false negative. Finally, accuracy, recall, precision, and prediction time are calculated using well-known formulas. Finally, for output, we plot both the predicted bounding boxes and the target bounding boxes over the image.
Hi, I am Arnav and I will explain SSD, the second model that we implemented. Now let's see what SSD stands for. SSD is a single shot multi-box detector. Single shot means that the task of object localization and classification is done in a single forward pass of the network. Multi-box is the name of the technique used for bounding box regression. Detector because the network not only locates the concerned object but also classifies it. In a convolutional fashion, the model evaluates a small set of default boxes of different aspect ratios at each location in the feature map with different scales as shown in the figure. At training time, the model matches the default boxes to the ground truth boxes. At test time, it will locate the box and give confidence score, which will actually be the max score out of all classes used in the training set. Now let's see the architecture of SSD. As you can see from the diagram, SSD's architecture builds on the architecture of VGG16, but discards the fully connected layers. The reason VGG16 is used as the base network is because of its strong performance in high-quality image classification tasks and its popularity for problems where transfer learning helps in improving results. Instead of the original VGG fully connected layers, a set of auxiliary convolutional layers are added, thus allowing to extract features at multiple scales and progressively decrease the size of input to each subsequent layer. Now let's go through the code. First we read the data in the Colab environment and get the bounding box coordinates, that is xmin, ymin and xmax, ymax. Along with that, we'll need to know the name of the image from where we'll be taking the snippet and the class name associated with that cropped snippet. In this section, I have defined the labels and the numeric value associated to it. Mask weared incorrectly is 0, with mask is 1, without mask is 2. Here I have also shown a cropped image with a person correctly wearing a mask, hence the label is 1. Here we define our model. The model is a sequential model used to classify the bounding box to get the correct label. Here we have 3 convolution layers followed by one max pooling layer and a dropout of 0.25. Then we flatten and again pass it through a dropout. The last 3 layers are dense, dropout, and again the last, which is the dense layer, has 3 nodes so as to get 3 scores and then get the final label. Here I have shown the training process. We experimented with different optimizers, mainly Adam and SGT, and with different learning rates and momentum values. Along with the datagen module and validation dataset, we fit the model over multiple epochs and thus train it for the mass detection task. Here we can see how the model is finding the bounding box and then predicting which label has to be associated with to that bounding box. We can see that the detections will be the XY coordinates of the bounding box, and the result, which will be the outcome of model.predict, will give the scores associated to the 3 classes, and we then take the argmax, that is the maximum score, and the label associated to it. These are the easy cases where we observe that the model did significantly better at recognizing the correct bounding box and the category. These are some of the incorrect cases or the hard cases. We specifically faced problem with images where people were walking in the background with or without mask, incorrectly worn mask, etc. Now we aim to improve the prediction on edge cases, take into consideration the orientation of the person in an image, improve prediction for incorrectly worn masks, try using face detection and then running a classifier, hyperparameter tuning, and testing the model on real-time images from a camera.
Hi, my name is Jipen, and I'm going to talk about our third model. You only look once, the YOLO model. YOLO is regarded as one of the most powerful, state-of-the-art real-time object detection system. The YOLO got 3 steps for it to finish its object detection. The first step is that the framework will divide the input image into a lot of grids. Then, image classification and localization are applied on each grid. Then, YOLO will predict the bounding boxes and their corresponding class probabilities for different objects, which are correctly wearing the mask, incorrectly wear the mask, without mask in our system. Last but not least, most of these cells and bounding boxes will not contain an object. Therefore, we predict the value PC, which serves to remove boxes with low object probability and bounding boxes with the highest shared area in a process called long-back suppression. After long-back suppression, multiple boxes will combine into one, which is the result. In our model, the dataset was divided into 80% for training data and 20% for test data. We used the PyTorch framework. YOLO version 5 simple model pre-trained on Coco was used. The model was fine-tuned on the training dataset. We use stochastic gradient descent as the optimizer. The loss function is the sum of the region proportional network and the region classification loss. When it comes to the results, the accuracy at the recall is around 40% and the precision is about 50%. As for the average prediction time, it is around 170 million seconds, which can be explained by the high amount of the grids generated in the first step, which caused a really lots of time. As for the bounding box labels, mask 1 correctly uses the blue box. Mask 1 incorrectly uses the orange box. Mask not 1 uses the green box. For the either cases and edge cases, we can see that large and clear faces and face masks can be easily detected and classified. However, for some faces that is small or oblique, or with some really special masks that is not more normal, there remains a challenge for the detection system. In the future, we are planning to improve the prediction on edge cases and improve the prediction for some incorrectly worn masks, and get more data to train and test our model.
Now that we have covered those three models, let us look at an implementation for real-time classification through your webcam. Here is a quick snapshot of the code used to implement the real-time webcam detector. The left image shows some of the packages we used, like PyTorch and CV2. Next to it, the middle image under the title shows the logic of the software. We first used a pre-trained model to find a face in the video, as well as its corresponding bounding box. Once this is found, we pre-process and pass the frame to one of the models discussed before to provide a prediction. This prediction will then change the color and label of our bounding box accordingly. The screenshot on the bottom right showcases what a typical output looks like, and the GIF on the top is an example video of how the software looks real time. We can see that the label when I turned on my webcam is without mask, and the bounding box is at coordinates 598, 428, 829, and 700. These coordinates represent where my face is and draws a box around it on the webcam. This code is extremely flexible and can implement any of the three models mentioned above. The only thing we need is the pre-trained weight file of each one. Simply plug in the model you desire and see the results.
This slide summarizes all our new and unique contributions in this project. We took three pre-trained models, Faster RCNN, SSD, and YOLO, and trained and fine-tuned these models on the training data to recognize proper mask detection. We additionally wrote code to calculate the accuracy, precision, and recall for each of these models and then compared them. We implemented a real-time webcam detector for masks that can be potentially be used with any face detector algorithm, including the ones that we trained.
Now that we have seen each of our models in action, let's take a quick look at what's left.
Here is the experiment results of accuracy, recall, precision, and average prediction time for our experiments using Faster-RCNN and SSD, and fully trained YOLO, and YOLO trained in 2 hours. And I will show our analysis on that later. Here is the comparison between Faster-RCNN and SSD and YOLO. From the table, we can see that the fully trained YOLO has the highest accuracy and recall, which is around 66.85% and 68.74%. As for the precision, the Faster-RCNN and SSD performs really good in that. They got a precision which are 85.71% and 80.6%. When it comes to the average prediction time, the faster -RCN and SSD also performs much better compared to YOLO. Their average prediction time is 15 milliseconds and 13 milliseconds. When it comes to the YOLO, it runs really slow. For the fully trained YOLO, it runs about 1300 milliseconds, and the YOLO trained in 2 hours, it also needs 800 milliseconds to process a picture. Comparing the fully trained YOLO and YOLO trained in 2 hours, we can see that a fully trained YOLO has a much larger increasement in the accuracy compared to the increase in the recall. So we can have the conclusion that the YOLO can easily learn the ability to do the recall. However, for the precision, it is harder for YOLO to increase that, and the final result of precision for the YOLO, it is also lower than SSD and faster -RCN. All in all, we have the conclusion that you should go for faster -RCN if you prefer precision. You should go for SSD if you prefer speed. If you prefer accuracy or recall for the system, you should go for YOLO.
In the coming weeks, we plan to implement 2 more models in order to make our solution as robust as